Solving inequations. Okay. Basically, two simple ideas when you're solving an inequation. And then we talked a bit about this yesterday. Find the critical points, because that's where it's going to change from less than to greater than and things like that. But you do that by, instead of thinking of it as an inequation, just treat it like an equation and solve it that way. And then test the regions in between those critical points to see, okay, where do I exist in this? So all sorts of different types. The simplest ones we started with, gosh, I don't know, when's the first time you saw linear ones? Year 7 maybe? A while back anyway. So we solve them like a normal one. The key thing, of course, remembering to change the sign if you multiply or divide by a negative number. Or, as I say, if you change the sign, you change the sign. So then we go up a level, quadratics or polynomials in general. So let's have a look at this quadratic one. I'll factorise it like normal, but I personally prefer to factorise positive x squareds rather than negative x squareds. I just get confused with the negative ones. So I've multiplied everything by -1, but of course that means I've changed the sign of the numbers, therefore I change the sign of the inequation. So now it's a less than 0. Factorise like normal, and that's where we get our two critical points from. We now know it's -6 and +1. They're not included, so we'll just have a hollow circle there, and we'll just test some numbers. 0 is always the easiest one to test, so let's have a look at that. 0 would give me -6, and -6 is less than 0. And the other thing I know about quadratic equations, because if you think of the graph, what you're talking about is a parabola. So it's either going to be in between those two critical points or it's going to be on the outside. So, well, we've just found out it's in between. No need to check the other regions with a quadratic. So there's our solution. Okay. Absolute value inequations we also then looked at. Remember the definition of an absolute value. Okay? It's A if A is greater than or equal to 0. But it's negative A if A is less than 0. So if you get something like this, the way we look at it is we say, well, it can either be 3x plus 2 or it can be negative 3x plus 2. So that's what our definition is saying. It can either be A or it could be negative A. Don't change the sign on the right-hand side, because that can cause problems with the inequality sign. So go with the definition, because then it will naturally fall out. So the left-hand side, move the 2 over, divide by 3. The right-hand side eventually will end up dividing by a negative number. So that's when we change the sign. It's just easier to go with the definition, either A or negative A, and just solve those two. Now let's have a look at those two. If I put that on a number line, I'm going it's less than, the first one's greater than or equal to -3rd. I should have coloured that in, shouldn't I? Oops, doesn't matter. At least I can do my answer. They were coloured in circles, of course, but we got our answer. X is less than or equal to -1 or greater than or equal to -1/3. All right, so that's absolute value ones. The good old pro numerals in the denominator. And we've seen lots of different ways of solving this. We've seen graphical ways of doing it. Yesterday we looked at, or was it the day before, we looked at moving everything to the left-hand side and showing it's always positive or always negative. So here's, I think it's actually the same one. 2 on x plus 3 is less than 5. I do it by looking for the critical points. So bottom of the fraction is critical, can't equal 0, so I know -3 is a possibility. Solve the equation rather than inequation, and I get -13 on 5. So, and again, let's just investigate the regions. And in this one, yes, -3 on the left-hand side, and on the right-hand side, a -13 on 5. And there's our solution. And it's like I was saying yesterday, that is the most successful method of doing them. Not the most common. Most people end up multiplying by the denominator squared and doing it that way and turning it into a quadratic. So numbers 3 and 4. So the absolute value ones can be turned into quadratics as well. Let's have a look at that. So back to the absolute value of 3x plus 2. See, if you square both sides, then you haven't got an issue with not the absolute value sign, the greater than or equal to sign, because square an absolute value, then it doesn't matter whether it's a or whether it's negative a. Square it, you get a squared. So if I square both sides, I'll get 3x plus 2 all squared is greater than or equal to 1. And eventually we can get our factorisation there. 3x plus 1, x plus 1 is greater than or equal to 0. And that would end up, because we're talking about a concave up parabola, aren't we? Concave up, when it's above the axis, well, that's on the outside of the two critical points. Just be careful when you're squaring, because sometimes it might create solutions that are not there, because you've changed the question into something else. So always check. Our pronumeral in the denominator, so in this case, you multiply both sides by the denominator squared. Again, do it by squared because you know that's a positive number, so therefore you don't have an issue with the inequality sign. And move to the left-hand side. Don't expand out. This is where people waste time using this method. Don't expand out because obviously x plus 3 is a common factor. So draw the common factor out and then you get the other one straight away. And well, we've got the same inequality again, except, there we go, our solution. X is less than negative 3, x is greater than negative 35. That's the most popular way of doing it. Not the way us super mathematicians do it. That's a mere mortal. Okay. Graphs. Can be handy if you've got the graph. If you haven't got the graph, not necessarily the most efficient way of doing it, unless it's a simple graph, of course. So back again, as I say, when we looked at left-hand side minus right-hand side. So when we look at it graphically, we're essentially asking, when is it above the line y equals 0? The x-axis. So any function can be done that way. So function x greater than g of x, we can do it. So when is function x above g of x? We don't actually have to create a new function. We can draw the two functions in and just simply say, well, when is f of x above g of x? Same sort of idea. So let's have a look at this interesting one. Absolute value of 5x minus 3 is greater than x plus 2. Okay, well there's the two graphs. The V1's obviously the absolute value of 5x minus 3. The straight line is x plus 2. So we're saying, when is the absolute value graph above the straight line? And we can read that off very easily. Just got to find this point of intersection. And I don't know if you can see from there or whether it's clear on your sheet or not. Unfortunately, that point of intersection does not land nicely on the grid. So we're going to have to solve the equation anyway to find the points of intersection. So let's do that. So we've got 5x minus 3 equals x plus 2. So x equals 5 on 4. Or it might be the negative, so it might be 3 minus 5x is x plus 2. That gives us x equals 1/6. So, all right, so we now know our 2 points of intersection, and we can see absolute value would be on the left-hand side of that point of intersection, which is 1/6, and on the right-hand side of that point of intersection, which is 5 on 4. As I say, not necessarily the best method, because in this case, I had to solve the equation anyway. I had to find the critical points anyway. I may as well just then have tested in between the points. Mind you, if you're doing it on a computer, things like Desmos does make this method more attractive because of course you can then click on the actual point itself and it'll say, oh, that's whatever number it is. Okay, so 3D, 3E, time to play.